Hi, my name is Annika, and today I'm presenting on behalf of our team on our approach to end-to-end multi-camera view passing to top-down object detection on roadmaps. The goal of this project was to predict a top-down view of the roadmap and the objects surrounding an ego car using the 6 images collected from cameras facing different angles on top of a car. With this problem, we had a large amount of unlabeled data. We constructed a pretext task that wide stitches the images, randomly picks one of the images to black out. We then use an autoencoder to try and reconstruct the missing image. Here's an example of one of those reconstructed images against the target. For the roadmap prediction, we now feed all 6 images wide stitched to the encoder, extract a latent representation shown in the red vector, and feed that to an MLP to predict the binary roadmap. Again, we can look at an example of a target against the prediction, where we're able to achieve an average threat score of about 0.9 on our validation set with this problem. For the bounding box prediction problem, instead of using the wide stitch images, we imagine what the perspective is like from the car facing to the right. And if you're inside the car facing outwards, your view is something more like this. And so we try and stitch the images to capture this representation and scale the stitched images to be 800 by 800. This simplifies the problem to be more of a standard object detection problem where the relative position of the objects correspond roughly to the relative position from the top-down roadmap view. So if we overlay the roadmap on top of the stitched image, the problem simply becomes translating the detected objects onto their true position on the roadmap, which is just a linear transformation. For the bounding box predictions, we use faster RCNN, but faster RCNN expects an image with 3 channels as an input, and so we combine these 2 inputs by using the 3 channels from the stitched image and the 1 channel from the binary roadmap, using a CNN, which allows us to output a single 3-channel image. We then feed this to the faster RCNN, where we replace the backbone with our own pre-trained encoder and predict bounding boxes. Again, we can look at an example of a target and a prediction. Notice that the model learns to place boxes only on roads. Due to computational constraints, this model was only trained for 5 hours, and it's far from being converged. Despite that, we were able to achieve an average IOU threat score on our validation set of 0.03.